So, okay. So today we're continuing with logistic regression. And we'll talk today a bit about diagnostics for logistic regression. So remember that our general setup is that we're modeling the log odds. And this, you might index this p by observation. Omit that for now. And we say something like, we have a baseline odds that's not dependent on the outcome of the predictor variables. So this is going to be the Boy Scout example. We have a change in odds, a log change in odds or an odds ratio that comes from some predictive variable like Boy Scout. We have some other odds that come from, say in this case, we have dummy variables for medium and high socioeconomic status. And so these have like a strange kind of exclusive relationship. And we have interaction terms. So this is Boy Scout and medium, and this is the interaction term for Boy Scout and high. And just let's write down this table to emphasize the kind of linearity that's happening here. So we have low Boy Scout, low not Boy Scout, low Boy Scout. The log odds are beta not. So there's always a beta not. Let me fill them in this way. M, Boy Scout, not Boy Scout, high, high, Boy Scout, not Boy Scout. So in everything, there's always this baseline in the log odds. And then depending on these other variables, we add in other factors. So if I have low and just Boy Scout, this would be beta not plus beta 1. This would be the baseline, where this is no and this is the 0 for both dummy variables. If I have medium and Boy Scout, I still have my beta 1. And if I have, so this comes from the B, so there's no beta 1 here, similarly. And then for the M, I get my M beta. So that's beta 2, and I also have a beta 2 here. And then I get another factor up here for the interaction. So that's the log odds for the mediums. And then for the highs, we have our beta 1 here for Boy Scout and nothing here for not a Boy Scout. We have our beta 3 for high. Plus beta 3. And then where I have both Boy Scout and high, I have an interaction term for beta 5. Okay. So all these log odds are just functions of the beta, and they depend on each other in a linear way. So if you have many, many of these, you can always compute missing ones by adding and subtracting. That's one of the exercises that we have.
Should include every interaction term.
Yeah, full model. I mean, sometimes we say full model just to mean a bigger model, like when we're comparing to the full and the reduced. But it'd be better to say saturated model, the one that has everything that you can throw into it. So the next thing we want to discuss is into lesson 7. That's continuous predictors. So from the way we've set it up, it should be pretty obvious how we're going to throw in conditional things. This looks almost like a regression. We have a nice linear function of some variables. If anything, it's a bit odd that these variables all take values 0 and 1, considering how we set it up. So to add in continuous predictors, all we're really doing is reinterpreting some of these x as a continuous or an ordinal variable. So like instead of taking a value 0 or 1, we'll take value 0, 1, 2, 3, 4, 5, whatever your scoring is from your ordinal situation. And we have this example, which is the Donner Party. It's a bit grim, but now if you go through Donner Pass on 80, if you continue on 80 west from where we are, you'll eventually get to Donner Pass. It's not quite nice now. There's a little park and place to park and a rest area. So they'd be fine if it was now. But in this example, we have 3 factors: age, gender, or sex, and survival. Survival is the thing we're trying to predict. And age and gender are predictors, or independent variables. So in this class, I've been trying to say predicted and predictor instead of dependent and independent, because that has another meaning in terms of independence and conditional independence, and I don't want to confuse those. And so what we're interested in doing is predicting the probability of survival, measuring the probability of survival as a function of age and gender, and then asking questions like, if we account for age or we ignore age, does gender predict survival? If we account for gender or ignore gender, meaning condition on or marginalize over, does age predict survival? And is there an interaction term? And how do we interpret that interaction term? So first, a marginal thing. We could look at survive and die, female and male. We're going to code female as 0 and male as 1 in this table. So we had some outcome that said, okay, of the members in this party, of which there weren't so many, only 45, 15 female and 30 male. The males died at a rate twice that of the females. Right? So there's certainly, if I were to compute a chi-squared, I get 4.5 with 1 degree of freedom and a p-value of 0.03. And so we could conclude that survival and gender don't seem to be independent. Females, on a relative risk measure, females survive twice as much, or you're twice as likely to have died as a male. And of course, by now, whenever we see a 2x2 table, and there's another variable involved, we worry about correlation and causation. We worry whether there's a lurking Simpson's paradox, that is this somehow explained away once we take into account the other variable, which is the age of the travelers. Before we do that, we could think about what if we just compared survival versus age as a kind of a 2x2 thing. Well, it's not really 2x2 because there's multiple ages. So we don't want to do, of course, a linear regression like given x1 beta naught plus beta 1 x1. So we don't want to do that, explicitly modeling the probability in terms of the linear function. That's not the GLM story. And this would give me probabilities that were not always between 0 and 1. So of course we want to do a logistic regression. That is, we want to model the log odds as being linear. Some baseline, odds of survival plus a variable, call it x1, I being the individual, or the row in the table if I'm grouped them. And this is going to be the age. So now we want to think about this as being continuous. It's not perfectly continuous because we just have years, but and if we plug this into R or SAS, we give it a formula like survive, predict survive versus age, and tell it what family to use, binomial with link logit. So in the software, typically it's not, though we've sort of separated out all these components. They don't set it up so that you could do anything. I mean, there's a formula like this, survival plus age plus whatever, that where you express the factors that you want to use, and then there's a family call where you explain which of the exponential families and which link function, and they're sometimes sort of disconnected in the sense that not all link functions make sense with not all families. Okay, so you fit that, and you get something like log pi 1 minus pi equals 1.8 minus 0.067. Let's call it 882. 0.67 x1i. Okay, so that's our prediction just based on age. So for example, at age 70, the predicted probability of survival is only 5%. At age 0, it would be 77%. This, of course, doesn't work quite right once you get to the very edges. But another way of thinking about this is what's the effect when we exponentiate the coefficient, the beta is beta 1, we get 0.94. And what that's telling us is the same kind of thing such a coefficient always tells us, which is that with each additional age, when the age variable increases by 1, we've multiplied the odds of survival by 0.94. The odds of survival are multiplied by 0.94. Of course, multiplying odds by a number less than 1 means the odds are going down. So the odds of survival are going down, so we're becoming more likely to die. That's the interpretation. And then when we put in the other factors, we're going to split that number up and try to adjust that number. So, yeah.
I was wondering, so whether, based on the result we got here, we can say that when the people get older and older, the chance of survival is an exponential decrease, right?
That's correct.
But how about the people with the newborn baby, say just a 0 age?
Right, so that would give you a number too. Of course, you could even plug in -1 and you'd get a number. The number wouldn't mean much though.
Okay.
Yeah.
How many levels of age are there?
There aren't that many. I don't remember exactly, but they were between, I think, 20 and 70 something.
Okay, because my next question is how many degrees of freedom does that model have?
Yeah, good question. Okay, let's keep going. Because we haven't done a hypothesis test or anything yet. Okay, so I think where she's sort of leading, Wiley, is that we have kind of a sparsity issue. Right, and this is very common when we're dealing with this kind of continuous data, and that is if I write down a table of age versus survival, there's going to be a lot of places where there's a 0, 55.3 or something. There was nobody who was exactly 55.3. Even if I make this better, there's going to be a lot of zeros in this table in that sense that it's sparse. And so what does that do? Well, it means that if I take literally the idea that I should think of age as a categorical variable, and I try to compute the degrees of freedom for this thing, and I try to compute like an x squared or a g squared for the full table, that's going to be nonsense, right? Because with all these 0 cells, our rule of thumb that we shouldn't have more than 20% of cells below 5 is like violently violated, right? There's nowhere near that, and that says that our asymptotic theory doesn't give us that these assumptions that these things are chi-squared should be expected to be anywhere near accurate. So we have to look at other options. So we'll talk about some of the other options to diagnose goodness of fit. So one is this Hosmer.
But excuse me, actually,
Yeah.
the data we have here, which is 45 observation. So in other words, so whether we select our sample actually based on bias. 45 data sets is good enough to make the estimation, right?
No, because there's too many zeros in this cell.
Okay.
So it doesn't matter what the total sample size is, it matters how many there are in each cell.
So in other words, the way how we select the data is the bias.
Well, we didn't really select the data. I guess you could think about it as a selection, but we're looking at a particular group. I mean, I don't know, it was selected by whoever was feeling adventurous in Wyoming, I guess. Okay, so the idea of the Hosmer-Lemma statistic is, I think I mentioned this before, is to group observations that give similar predictions. Group observations giving similar predictions, and therefore essentially compress the table until I have a number of cells such that the chi-squared approximation works okay. And of course, this is still fairly simulation instead of theory-based. And the other thing we can do is to fit a bigger model and focus on the changes in G squared, which are still reasonably well behaved. And here, if you do the Hosmer-Lemma show with something like 8 groups, it gives a reasonably good fit. There's this question, how do you choose groups for Hosmer-Lemma show? It's kind of a dark art, I'd say. So I think in the original paper they said, I choose around 10. But that's a little bit too specific, although you'll often see people choose around 10, or the software will choose around that. Another rule of thumb might be something like number of predicting variables plus 1. So not the number of states, right, the number of cells, but just the number of variables. And probably want group size to be greater than or equal to 5 per cell, mostly. And so in this case, it turns out that all of those, so suppose you did this, you took this really literally, right? And you said, well, let's just group them until, and they should all be around the equal size. Then this would give you something that was on the order of the grand total sample size, right? Like that divided by 5 or something. And it would probably also satisfy that it was bigger than this. So it's kind of a rule of thumb, and these are sort of bounds for that. Right? I wish I could tell you that the theory was better, but it's not that great. Okay, but anyway, the Hosmer-Lemma show will do something that works, and then we're going to look at some of the other models and see whether the increase to a more saturated model or a bigger model gives a significant change. So the next question we might ask is, accounting for age, are women more likely to survive? And so for this, we can do a comparison of models, and that still works okay. That is, we're looking at a null hypothesis, zero out a coefficient, in this case gender, and we're considering that relative to alternative hypothesis, which is leaving that in. Our usual nested model comparison, and we're asking, we have a delta G squared. It has 1 degree of freedom, because we've only changed 1 coefficient, and we can ask whether that's significant. So that model would look like log pi, 1 minus pi, is equal to beta naught plus beta 1 x1i, where this is the age of person I. And then we add in another factor for gender. And we're coding like that. And so now our question is just, does adding this beta 2 significantly improve the fit of the model? So for that, we just need to compute our g squared. And we don't need to care what the degree of freedom is for each of these because we're not testing them directly, we're just testing the difference. 56.3, 29, 1, 51.256. So the difference is 5, a little bit more than 5 with 1 degree of freedom. And that's enough to reject the null hypothesis and say that the gain in fit, when we go from not accounting for gender to accounting for gender, is significant. So even after accounting for age, the effect of gender is significant. And then if we fit that model, let's see what that looks like. So that one looks like log pi 1 minus pi. It's 3.2 minus 0.08 age minus 1.6 gender. And if you exponentiate, you get an odds of survival baseline. You get that the odds are multiplied by 0.925 per year. And we get that the odds of a male surviving are 0.2 times the odds of F. Okay, so the 0.94 became 0.925, and then there was some change for gender. Yeah.
I was wondering, for the way, the reason why we propose this model, whether we are assuming that the two interaction terms between the age and gender is non-significant, right? Based on that assumption, we propose this.
No, we haven't talked about, right. So this is the model without interaction. The next model we want to test is the one with interaction.
Okay.
Right, so
which one is so for our one, usually we should put the full model as every one factor interaction, one factor variable, and also put the two-way as the interaction variable. And then after that, we say if the two-way interaction term is non-significant, and then we can propose this model, right? I was wondering what is the right order to propose our model.
yes, you can put the model in different orders, right? I mean, that's one of the exercises, in fact. Compare forward selection and backward selection. Right, that's what you're asking. Is it better to go forward, start with a simple model and build a more complex model, or is it better to start with a complex model and subtract things? And the answer is yes. Both of those things make sense. Depends on the, and there's sort of papers about why each of those is great.
I have a question.
Yeah.
I think we already covered the part, but I wonder how do we decide the degrees of freedom of each model, like age and age plus gender?
Well, right now I'm punting on that, right? I'm not even saying what those degrees of freedom are.
Okay.
I'm only looking at the comparisons because of this awkwardness of the sparseness.
So is this considered a conditional model?
Yes, it's a conditional model because, in the sense that it's a logistic regression. So we're asking about a dependent variable conditioned on the other things. Is that what you mean, or do you mean it's a conditional independence?
Either.
Well, let's see. So we have survival, and we have age, and we have gender.
Okay, yeah.
So it's not this model, right? Which as a graphical model would be like that. It's this model. It's not this model. Right? This model says age and gender may be related, but we only care about the effect of age. That was the first model I looked at. So it's not this conditional independence model. It is this conditional independence model. It's not this saturated model. Yeah.
So, can we just calculate the degrees of freedom based off that? Like,
Well, but it's yes, but you're asking a little bit different question. I mean, the problem is that, so the problem is how many, should I give this thing if I have, well, if age is truly continuous, the degrees of freedom will be infinite. Right? If age can take on, if I measure age in nanoseconds, the degrees of freedom is really big. Right?
so that we basically just interval that up, just turn it into.
Right. So that's a sensible thing to do, right? Is to say, okay, well, what we're going to do is we're going to turn this age continuous variable into an ordinal variable. We're going to compress the intervals until they're small enough for our statistics to work. That's fine. That works. Right? And that's sort of another approach. I know we're trying to put a coefficient directly on the year, and that's sort of reducing it from a continuous and making it into instead just an ordinal variable. And if you did that and you reduce this number small enough that your cell counts hypothesis was satisfied, there was enough in each of the cells, then your chi-squared, your Pearson would work, then you'd get a degrees of freedom. And that, in some sense, that's kind of like the, if you did that model where you intervaled up age, and you kept messing with it until it was just as good as the one that was continuous, in some sense, that captures all the information, and that should be sort of the true degrees of freedom. Okay.
Yeah, excuse me. One more quick question. I was wondering, so if here we treat the age as a continuous variable, so in other words, we have a really we have a lot of power for our model, right? So I was wondering, so if we treat the age as a continuous variable, in another word, we'll have a lot of advantages over converting the continuous variable into a categorical variable. Right?
Yeah, in principle. I mean, but
we'll have better. We'll have to really.
Yeah, it might work better, but it might not. I think one of the lessons that you'll find if you mess with this data enough is that you'll find that as long as you use enough chunks, in many problems, chunking it up, making it an interval, doesn't really lose much power. And that's one of the reasons you see that done a lot in studies, right? They break something like the heart study, right? They break cholesterol up into groups instead of just putting in the cholesterol by itself. So yeah, I mean, it's an empirical question. Okay, so now I want to add the interaction term, which means we're going to this model, the conditional version of it. And our new model is log pi 1 minus pi equals beta naught plus beta 1 age. Let me just write age. Plus beta 2 gender plus beta 3 interaction age gender. So it's better. Okay. So this is our model with interaction. And now we want to ask, our null hypothesis is that this interaction term is 0. And our alternative hypothesis is this full model in the sense of this model, and then that's not 0. Oops. Beta 3 is not 0. So we have to just augment this table of the minus 2 log likelihoods, age 56.3, age and sex, but not interacting, 51.2.3, and age plus sex plus age times sex, and that becomes 47.4. And then we have a delta G squared between these two of 3.91, which is sort of weakly significant. So it's just significant at the at 0.05 level. And so what does this interaction term mean? So that says it's worth including, if just worth including. So because of all the exponentiating going on here, that addition becomes multiplication. And so what the interaction term says is the effect of age is different for men and women. So for each additional year, for each amount that the age variable goes up, the odds of survival for women is multiplied by beta 1, e to the beta 1, and the odds of survival for men is multiplied by e to the beta 1 plus beta 3, the interaction term. And if you fit it, okay, so we go from a 0.94 with only age to 0.925 with both age and gender but not interacting, and then that number splits into 0.824 for female and 0.968 for male. So what that says that females are more likely to survive, but age reduces their survival probability more quickly. Like that. This is F, something like that, and that's M. The slope is steeper, even if it's overall higher probability of survival.
One more question. So I was wondering if people ask us a situation, say, can we use, if people ask us, if we want to apply our result to a newborn female baby, can we think first, based on the result, to say the female, newborn baby has a really higher chance to survive. So do you think
that's what the model would say.
To explain to some people?
Well, that's up to the user of the model. So the model can't really make decisions like that for you, right? It's a very simple, it's a simple formula. Okay, so the next thing I want to talk about is diagnostics for the model, for logistic regression. And diagnostics are more or less an attempt to port the ideas that you use to diagnose linear regression to logistic regression. So we can look at residuals, Pearson and deviance, which we'll talk about in a minute. We can look at leverage. And another thing we can do, which is sort of more natural or doesn't require kind of translating ideas from regression and sort of forcing them into this, is effects of removing things. Almost like non-parametric. So in other words, a nice way to do diagnostics is just to look through your data, remove each individual observation, and ask how much does it change when you move that observation, right? If it changes it tremendously, if your answer changes a lot, that means that observation is like really objectively influential, right? It's an important observation, maybe that means it's an outlier. And for that, we might look at, for example, beta, which is called the DF beta procedure in SAS. And this says for each parameter, so there's a lot of these, beta naught, beta 1, and so on. For each observation, how does the parameter change? Maybe in the Donner Party there was one person who was 400 years old, and that's just messing up everything. Obviously, this is going to produce, if you have a lot of parameters, this is going to produce a lot of numbers. And it makes more sense when there are only a few parameters. You can, there's a thing called, well, at least called in SAS, called C-bar, which you can summarize these things. So there's various ideas for how you should, if you find this to be too many answers, you can sort of sum that all up over all the parameters to get an effect that's due to each one. And then sort of, since we reduce so many things to measuring changes in G squared or in Pearson, we can ask this: how does each data point change our Pearson or our G squared? So that's, if I delete a point, how does it drastically affect the fit or not? And that's a pretty good measure. Okay, so to talk about the ones like residuals that are essentially drawn from linear regression, let's sort of swing back to thinking about linear regression. So linear regression is a generalized linear model with a very straightforward systematic piece. And the link function is just the identity. And it has this extra parameter, from our point of view, compared to like binomial and Poisson, has this extra parameter sigma to account for changes in variance. So it has a mean structure, which is the linear component, the systematic component, and then it has this spread. And we assume that this is true, and that there's only one sigma, so that there's homoscedasticity. That's an important part of the assumptions under regression. And so we often look at the residuals. We have our true value yi, and we subtract our estimated yi, and we look whether it's we look at the spread of those values. And if there's any sort of systematic pattern in those other than being a nice horizontal band, that's sort of evidence that there's something potentially wrong with our regression. Right, so we want it to look like this is yi hat, which in the case of linear regression is just x transpose beta. And then this is the size of the this is the residual itself, Ri. And we want it to be a nice, like, horizontal band with no big, if I have values like this, these are outliers. And we don't want to see that. If we see curvature, like that looks like that or something. So that's bad. That means that the relationship that we've assumed between predictors and predicted variables is not linear. There's another systematic component to it. And so maybe we need to throw in a link function, or maybe we need to transform our predictor variables in order to get something that's sensible.
Yeah, I was wondering, for a second case, can we just add some white noise and then to...
No. This means that your linearity has failed. The other things that can happen is that, like, the spread could be wider in some part and less wide in other parts, which means that your homoscedasticity assumption has failed, and so on. So we want to make some analogous plots so we can look at the data for logistic regression. But we're faced with a choice in that the definition of a residual, there's nothing quite so natural as we have for this case, right? I mean, if the outcome is not this nice continuous variable that's predicted linearly like this, it's like 0 or 1, and so we have to do something, right?
Well, yes, excuse me.
Yeah.
For a second case, so if investigation happens, can we just take a log to stabilize and stabilize the variance? How we take the model?
Maybe. I mean, that's sort of 501 linear regression tells you about the different techniques you can do to try to fix that. So we have our link function, which is kind of an extra step in the logistic regression. And we have our variance, which is, by design, heteroscedastic, right? I mean, it's inherently fails that. And so it doesn't make much sense to use the literal residuals, but we can do residuals for Pearson and deviance, right? We can do the residuals where we broke up the computation of deviance or Pearson chi-squared into a sum of things, and we can use those residuals and look at those. And the idea is that that's somehow similar. That is, I want mu here to be, I didn't write that down. So what's that? Let mu I hat be n I p I. So we take what we estimated the count to come out to be, what we would predict in like a cell of the table under a binomial, and we want to subtract that from what we actually saw in the table, and then divide by our variance. Or we can compute the deviance residuals. I forget what letter we use for those. And the idea is that when we have a large enough sample, these things look something like the standardized residuals in linear regression, right? We said earlier in the class that you can think about those residuals as having an approximately normal distribution under suitable assumptions. And so it's not crazy to look at a graph which is the same on the bottom, except that this is not the expected mean anymore. It's just the linear component. And graph that against the Pearson residual. And then we can ask the same questions. And look for something which is roughly, because now we've transformed to something which should be approximately normal. And we might need to scale these to fix the variance. Unless I had variances in there. They're already scaled, so we should look for something similar, which is horizontal, roughly horizontal, and passes or fails the same sort of tests that a regression test would. So we don't want to see outliers. We want this. Outliers have the same kind of meaning. Curves means that in this case, it's not quite a failure, but it's that our link function might be off, or the x's need to be transformed. Maybe we need to take the log of the x's, or one of the x's, or something like that, in order to get this to look clean. So some xi might have to go to log xi or something.
I'm wondering, here, because based on the given the variance, it's a binomial distribution. But originally we see that yi actually is IID normal distribution.
No, those are totally different yi's. I was talking about regression here, and now we're talking about logistic regression. Sure. And remember, so this is one of the things that shows up in the homework, and I noticed confused a couple people. We're allowed to do this in generalized linear models. We're allowed to take the variables that go into our systematic portion and transform them however we like in order to make the model work. So it's a very broad class of models. And of course, if we change the link function or we change these, or if we rescale the parameters by hitting them with some nonlinear function, the interpretation changes. our nice, clean interpretation in terms of multiplying odds ratios, which is already not that great, becomes even more complicated. However, we have to pass it through whatever function we did. So for example, if we change the link function to log of pi equals xi transpose beta instead of logit, then e to the beta I should be interpreted as a relative risk instead of as a log odds ratio. And there's some further ad hoc tests that people have proposed for testing fit, like throw in the squared value of the predictor function and see whether, and do the fit again. And if your fit improves, then well, probably something was not right to begin with. Okay. So the next topic we want to discuss is overdispersion. So overdispersion, came up early on in the class. We talked about how for a series of dart games in which my skill level is changing, or where I have different people playing and I don't know who's playing, something like that, I'm going to observe a variance which is higher than would be predicted by a simple binomial model. And so in the GLM context, our hands are tied in that once we've predicted the mean or our measure of centrality, like our p for each observation, our variance has also been given for us by the form of the functional form of the exponential family. In a linear regression, we have this extra free parameter sigma squared that allows us to change variance and our measure of centrality differently. And so the idea of overdispersion is basically take your nice binomial function or your Poisson function and just hack it by adding another parameter to account for this extra variation. And I think you should really think about it as that in almost all cases, it's really that there's something you didn't observe. There's a variable that you're summing over that you didn't get into your data. And overdispersion is kind of a way to adjust your model so that you can still correctly estimate the mean and you give up your understanding of the variance. You saying, I don't care what that hidden variable is. I'm assuming that it doesn't do anything important, doesn't make the effect go away. That's usually what's going to be causing this kind of thing. So, of course, it's also possible to have underdispersion, although that rarely happens in practice. Okay, so what happens to our measures? So when it happens, when it's present, our standard errors for our coefficients are off. Our test statistics, any other test statistics, hypothesis tests are off. And our goodness of fit is off. And so part of what we're doing is by estimating this extra sigma is to fix this. And because there's a goodness of fit problem that's happening, so if you think about the goodness of fit statistic that you're going to get, you expect that this goodness of fit x squared or g squared is approximately equal, like its mean of that such a variable is just the degrees of freedom, right? And so this is one of the awkward things about overdispersion. So it's sort of hard to distinguish between overdispersion and just a poor fit, right? Because what happens is that if there's overdispersion, this number will be bigger, which looks like a poor fit. And we're going to adjust it. We're going to sort of force it to be a good fit by creating a new, by introducing this new parameter sigma, which is based on how much larger this is than what we expect. So we're kind of forcing the model to fit. And so it's an adjustment that is fine to do, but you should sort of have a good theoretical reason as to why there's overdispersion. Like, you're measuring the traffic patterns or something, and you know that you're summing over a variable like time of day or skill level or something like that, and kind of know what the parameter is. You're okay with it being excluded from your data, and you don't think it causes any fundamental problems, because otherwise you can sort of force things to fit by just throwing in this extra parameter, or force an apparent fit. Okay, so
I was wondering, so regarding to the overfitting, I was wondering whether we're expecting the chi-square is big enough or p-value is small enough to reject the null hypothesis. So if the chi-square is big enough, it's okay for us, right? Because we want to reject the null hypothesis anyway.
no, it depends on what exactly you're asking. I mean, when it's big, it says that the null hypothesis doesn't fit well. But we're thinking of it as a test of model fit. So we're sort of forcing not the null hypothesis, but the thing whose goodness of fit is measured by this to fit by overdispersion. So let's see how that works. So how do we make this adjustment? Well, so we have our link function, which is just by the functional form of logistic regression, and we have a variance function which is also fixed and given to us by the binomial functional form. And now we're going to include a new parameter. Instead of the variance being this, it's going to be sigma squared times this. So this is the one under the binomial hypothesis, and now we're going to just add a multiplier to it. Okay, so when sigma squared is equal to 1, this new parameter, then it's not overdispersed. And when sigma squared is greater than 1, we have overdispersion. And if we knew in advance what this sigma square was, we would be able to squared can fit our coefficients in a consistent, asymptotically normal way. Right? We can fit it, and it would satisfy all of the usual conditions. And part of the point of this is that if we now estimate sigma squared, we get the same estimate for our coefficient as we would have under that case. So it's kind of like, how do I say this? So you have a situation where the single parameter that you're interested in affects both variance and mean, like probability of success, average probability of success. If you try to estimate both variance, and you try to make it fit both variance and the measure of centrality or the probability of success at the same time, it's going to move your estimate toward one that is sensible for the variance, right? So like it will move, so if you're overdispersed, it will always move your p in whichever direction will increase the variance, resulting variance, right? If we add this sort of slack parameter, sigma squared, now the estimate of success is free to kind of stick where it needs to be and doesn't get pulled toward the one that would give it higher variance. So to actually estimate this thing, again, what we're basically going to do is just use the way that the failure to fit. So our estimate sigma squared hat is going to be the Pearson divided by the number of parameters. This is the number of rows or groups. In the darts example, this would be the number of games. Right? So these are the number of binomial parameters that show up in our model, the binomial distributions that show up in our model, not the number of observations, because then it would just be binomial, but or Bernoulli, but the number of, right, so like if I write my table like class, number of successes, total number, right? Class 1, class 2, class 3, class 4, then big N is the number of classes. Okay. So it's not the total here. This is not that. This is something different. It's just the number of classes. Yeah.
Everything very clear to me, except one thing. So I was wondering, so the way how we group the classes, whether it's saying we expect there's a very high variance in the class, but there's very low, or there's no.
We're not saying anything about how to group the classes. You can think about this as, someone hands you a table. Someone hands you a table with some number of, 5 classes, yi, ni, and some parameters. This is just given. We're not talking about grouping it at all.
Okay, so I was wondering, actually my real question is going to be whether we expect there's a very low variance in the class, but there's very high variance among classes.
No, we're just saying that we're in this overdispersion setting, so what we're saying is that the variance, the total variance is larger than we would expect if the binomial. So you should think about this example of darts, where I play 1,000 games of darts, 10 throws each. The variance of the whole, my estimate of the variance is going to be higher than it would, or the variance is going to be higher than it would be if it was binomial, because the underlying parameter p is changing. Okay, so once we estimate sigma squared, we also have to adjust our test statistics in order to scale for that. So, so for nested models, instead of delta g squared, we use delta g squared divided by sigma squared. Instead of delta Pearson, I divide by sigma squared. And so on. And the covariance matrix for my estimates of beta becomes sigma squared x transpose wx minus 1. So in other words, we take whatever standard errors we would get on the other thing and we adjust it by sigma squared. So our confidence intervals on our betas get larger, and we need to just make this adjustment, divide by sigma. Most of our tests are based around this, so we're just mostly doing that.
Would we expect this arrangement just to look like
Is what?
without overdispersion?
What is the variance matrix?
No, the covariance matrix for beta.
The covariance matrix for beta.
So what do you expect it to look like without overdispersion? So you don't have to.
Yeah. I'm sorry, I don't remember at the top of my head how to. So somewhere in there, in the book and in the world, there's the how you derive that covariance matrix. I don't think I ever discussed it, but I just don't remember what it is.
Yes.
It has to do with the multinomial covariance matrix.
Oh, okay.
It's kind of originally comes from that, but you have to adjust it in various ways. So, yeah.
So I was wondering, related to her question, so I was wondering whether for the covariance matrix, whether saying the diagonal, the variance, on the diagonal going to be sigma, if they have from the same distribution, but for the off diagonal, the element going to be, say, sigma ij. Is that true? Because for the
You're saying is the notation, so
Yeah.
on the diagonal, often we write like sigma, sigma, and off the
Yeah.
diagonal, sigma, ij.
So actually, if I mean all the classes from the same distribution, so the sigma ii on the I should be the same, right? I mean, because they are they're from the same distribution. That's the thing that I was thinking about. Whether all the elements on the diagonal, I mean part gonna be the sigma, gonna be the sigma, but for the off diagonal part gonna be sigma ij, which is totally different.
Yeah, I don't think so. So the covariance matrix we're talking about here is this one. So when these are the estimates of the parameters in the model, these numbers are the variance. So if I was going to do a hypothesis test, you know, for an individual parameter or get a confidence interval, I would look at its covariance, its variance, and then I can think about the covariances. So these are the numbers that I'm saying need to be adjusted. If I add an overdispersion parameter, I have to multiply this matrix by sigma squared. Yeah. So yeah, everything gets multiplied by sigma squared. Okay. So the last topic that I want to mention just quickly, and I'll wrap up for today, is this ROC curve. So now we're getting into what feels a little bit more like the way kind of machine learning people would think about classification. So logistic regression and multinomial logistic regression are, you think about them as being classification problems, right? Like I have a bunch of features, I have a bunch of things that I can measure about some situation, and for each one I combine all that feature information, I hit it with a function, and I make a decision. Is this person going to survive or die? Or is this, you know, should I label this thing, you know, red or blue? Whatever. So I have to make a classification decision. And yes or no. And there's different ways of measuring the accuracy of that classification decision. One of them is this idea of an ROC curve. And the ROC curve takes a false positive rate, also called 1 minus specificity, and a true positive rate, also called sensitivity. So you try to decide if look at a test and decide whether or not someone has a disease, or decide whether or not there's a Japanese airplane in the sky being picked up by radar, which is where the name comes from. And what you think about is you take all of these factors, right, that I plug into my logistic regression, and what happens at the end, right, I have case I, and I get log pi over 1 minus pi is equal to some linear function of the inputs, right, of the things that I've observed. And from that, I get my expected pi, right, which is a number between 0 and 1. And suppose I'm not happy with that, I have to make a decision. You know, do I scramble the fighter jets to try to intercept these planes or not, right? That means instead of looking at a value between 0 and 1, I have to make a call. Is this thing 1 or is it 0, right? If it's a test for a disease, I have to make a decision, you know, do I treat the disease or not, right? And how do you make that decision? Well, usually you pick a threshold. I pick a number between 0 and 1, like 1/2. Right? So suppose that's a pretty reasonable threshold. Say if the p is greater than 1/2, then send the jets out. If it's less than 1/2, then don't. You know, if I want to be really conservative, I could say, okay, if p is greater than 0.9, send the jets out, and if it's smaller than 0.9, don't. So I want to, you know, if it's expensive to take the action, right, or I think that very few things actually have this property, right? The test is very rare, I'll cut it off. The disease is very rare, I'll have a high cutoff. If I want to be conservative in the other direction, I might say if it's anything greater than 10% chance of of being true, then I want to take the action. Right? So what a receiver operating characteristic threshold curve says is, as I increase that, so if I start out at a threshold down here, right, I get absolutely no false positives because I never scramble the jets. Right? Way out here, I get lots of false positives because I always do it. And in between, there's a choice of thresholds. So you can think about this value as being the false positive rate, or you can think about it as being the threshold. They're on a different scale, but they go in the same direction. As I increase the threshold, I capture more of the true positives at the cost of error, right? So if it's absolutely random, then it looks like that. And if the better my classifier is, the higher this is, right? If I have a really great classifier, I'll capture almost all the true positives at a very low false positive rate. But there's always a trade-off when I move this threshold. And so the ROC curve is a sort of a diagnostic for how good your model fits or how accurate your predictor is. It says, how close is this curve to the top? One good way to measure that is just to say, well, what's the area under the curve? So the area under the curve. And that's an often reported metric for the quality of a logistic regression or other sort of classifier. How close does it get to this ideal classifier that always gets the right answer without any cost? Okay. So that's that, and that's all for today. So your homework is due tomorrow. Everyone should have gotten an email from me about the project. The project is also posted on Angel. So you should think about what you want to do for your project. 9 times out of 10 or 99 times out of 100 what people do is take a data set they care about and apply the techniques. You'll find that they sort of work, but you have to do some thinking to get them to work. Also perfectly fine is if you want to try a new technique or write up a new technique that doesn't have to do with your particular data set because you don't have a data set, that works too.